Hello. Our next lab will introduce concepts and provide opportunities to experiment with methods for force and displacement measurement. These are methods and concepts that most of us are introduced to pretty early in our career, and they're very important, especially for mechanical engineers. So what we're going to do first is, at least in this lecture, talk about displacement sensing devices. Strain gauges in particular are important. We'll also talk about LVDTs, which are an inductive type of sensor, and also another type of non-contact sensor that we'll use, which is a laser displacement sensor, which is an optical type sensor. It turns out sensing displacement is important, especially because it's central to how we design most of our force sensors. So we'll talk a little bit about how we do that, and then we'll really turn and talk about strain gauges and how they're used to design force measurement devices, especially with beam type configurations. Then I'm going to talk a little bit about the lab study, and in a separate video I'll discuss some of the pre-lab preparation and the lab evaluation. So this slide really just shows overview of the different types of methods used for measuring displacement, if you like, motion, distance. Mechanical methods are essential. We use them for calibration, quick measurements, and so on. The contact type sensors are like the LVDTs, and we'll talk a little bit about those later. And in another lab, talk about inertial type sensors for motion, accelerometers. Strain gauges can be classified as a sort of displacement sensor. You are measuring strain, which is how much you are stretching, if you like, a piece of material. And then there's a whole class of other types of non-contact sensors that are optical, magnetic, and capacitive. So let's talk a little bit about strain gauges. Strain gauges are resistive type sensors. What they do is take advantage of how resistance changes as you strain a material. And we again classify this as a resistive type sensor, similar to the potentiometric sensors that we saw in another lab. Strictly speaking, strain gauges are piezoresistive, and the way they work is it's really just a piece of some kind of metallic material. It could be semiconductor, as I'll discuss shortly. This shows a typical geometry, if you like, for what's called a foil type strain gauge, which is the most common type. And as you can see, there's two terminals. It's basically a resistor as it stretches with whatever kind of specimen it might be attached to. Its resistance changes. There's different types of strain gauges that have been used in the past. The very first types of strain gauges were actually just wires that might be turned around different posts, and as a structure was stressed, the wire would change resistance. But the foil type is this type that you see here. This substrate is mounted right onto a specimen. Semiconductor strain gauges have become very popular since the 1960s. These are essentially like the pressure sensor that we used in the previous lab. That was made using microelectromechanical type device, and in those cases you might have strain gauges that are directly embedded right into the semiconductor material. So you can also buy semiconductor strain gauges to use for different applications. Like any sensor, the strain gauge has sensitivity, and what's important here is how much the resistance changes as you strain the gauge. And that ratio is defined as the gauge factor. The gauge factor can be shown to be related to the sort of geometric change in the material, which is related to Poisson's ratio and also to a material part. So most sensors will have this kind of basic mechanism where you see a change in geometry and a change in material. You see Appendix A. I won't go over that derivation, but that shows you how a gauge factor is derived for a uniform conductor. So you can see the gauge factor is related to the strain, and it's the change in resistance per unit resistance, right? So the gauge factor then becomes sort of a property of the strain gauge that you are using. Typical values, and this may be a little hard to read here, but typical, very common type of strain gauge is a nickel chromium types, maybe 80% nickel, 20% chromium, and those have gauge factors of about 2. 2 is a very common gauge factor. And then you see there's other types. Nickel copper has 2 also. Platinum has a value of about 5. And then there's also platinum iridium. You're getting gauge factors up at a level of 5. But the semiconductor strain gauges are pretty high. You can get really sensitive strain gauges using semiconductor material. And there's a lot of different types of strain gauges out there that you can find for different types of strain behavior. This photo here shows you there's different types of geometries for detecting different types of strain in material. All of them have a gauge factor. They also need to be selected based on the material that they're going to be mounted on. And as I said earlier, the semiconductor strain gauges have the highest gauge factor, but you do have some disadvantages in that the output is typically not linear with strain, and also they're very temperature dependent. So how do we use them? Well, the strain is being monitored by monitoring the resistance change. So it's an electromechanical conversion. You're going to be monitoring, how R changes, not necessarily the value of R, but how much is changing from the nominal value. So we use that basic relationship for the gauge factor, and here's a little example. Say you had a situation where you strained a material on the order of about a microstrain. You can estimate that the change in resistance for a gauge factor, say of 2, given a microstrain and a nominal resistance of about 120 ohms, which is common, you see that you get a very small change in resistance. And this is what we can measure. Well, that's way too small. So detecting this kind of a resistance change is very difficult. So it turns out really we use different types of signal conditioning to detect strain. And we also try to design the materials, the structures that we put strain gauges on so that it's sensitive enough so that we can detect it. And so we'll talk a little bit about that. First, in terms of the signal conditioning circuits, you can think about the potentiometric circuit that we saw before. That's the simplest type. Basically, put a strain gauge in a circuit with some kind of power source, voltage source, a series resistor, and you measure the voltage across either the strain gauge or the fixed resistor. And that's a real simple voltage divider type circuit, but really that doesn't turn out to be as effective as other methods. There's other types of balancing potentiometric circuits, and the most common really is a bridge type circuit. And in a bridge, which you've probably seen in a circuits class, involves taking 4 resistors, and these could be 4 strain gauges, and you power the bridge, so you put an input voltage and then you measure the output. So in this configuration shows actually a null detector, a specific case. Don't worry too much about that, but in this case, for example, you would have a known ratio between these 2 resistors. Maybe you don't know what this resistance is, and then you could adjust this resistance until you had a null output, and that's how you would use a circuit like this. It's not necessarily how we're going to use it, as I'll show you in a second. So when you do have a bridge with the 4 arms having resistive elements, strain gauges, for example, we refer to that as a Wheatstone bridge. I'll show you shortly. You can have an impedance bridge where these elements, 1 or more of these, might be capacitors or inductors. But in a typical configuration, again, you put voltage in, say, across A and B, and you measure the output across C and D. And we say that this bridge is balanced when the ratio of the resistances of any 2 adjacent arms, so for example, the ratio of R1 to R2 is equal to R3 to R4, or R1 to R3 is equal to R2 over R4. When that happens, when those ratios hold, then the output is 0, and you can show that. We won't do that here, but you can show that that's the case. As I mentioned, impedance bridges, a more general case, the impedance bridges are used in a lot of different types of sensor signal conditioning circuits. To just the way we need a Wheatstone bridge to detect changes in resistance, we use impedance bridges to, say, measure and detect changes in inductors. So you might have an inductor here, or a capacitor, or a combination of those. And when you have capacitors or inductors, typically you're exciting these bridges with AC signals, not DC signals. With Wheatstone bridges, we usually are powering them with DC type power. So for those cases, consider now, take the opportunity to talk a little bit about inductive sensors. The reason we want to do that is because there's a lot of different types of displacement sensors that use this principle. So remember when we talked about resistors being able to act as sensors by taking advantage of some change in the geometry. Remember the potentiometer circuit? Or change in material. If the material property changes, say because of temperature, you have a thermal or a thermistor type device. Similarly, with devices that store magnetic energy, so like in this example, say you create a magnetic flux in this ferromagnetic core. You can envision then if I could detach this core, then as this gap changes, I'm going to get a change in the stored energy, and I can detect then what that air gap is, and in that way you can create displacement sensors. So this shows an example. You might have a magnetic field built up, magnetic flux actually flowing through this magnetic circuit, and as this air gap increases, you can detect that inductance change, and by that infer what that distance is. And so you can get very sensitive types of devices this way. And that's in fact how the LVDT works. In the LVDT, this shows a schematic where you have a core moving within 3 different coils. So in the primary here, you might have an oscillator circuit. So you're pumping in AC, an AC voltage here, creating magnetic field here, and it's coupling into these other secondary coils in different ways. So depending on the position of this core, right, you can detect a difference in this voltage. Again, this is AC, so you need some signal conditioning here to then infer where this core might be, because you're going to now be getting different, as the core moves, you couple different amounts of magnetic energy into this core, so you get a difference in this. You get a different difference output voltage, and in that way you can build a basic sensor this way. You might find in reading about different sensors, say it might refer to these as they're either inductive, or if you use a magnetic term, it's either varying inductance, or it's a variable reluctance type sensor. So for example, you might read, oh, that pressure sensor uses variable reluctance, and that means that it's using this kind of principle where there's a displacement that causes a change in the reluctance, which can be detected and used to infer, say, pressure from that. Here is a typical calibration for an LVDT from this is a Shavitz type sensor, and this just shows you the core here, and that core slips into the inside of this tube here. You have the 3 coils inside. Many of these LVDTs now have all the built-in signal conditioning, power supply and so on, sorry, not the power supply, but the oscillator, you would basically give this just a DC power, and the circuit for creating the AC, for example, would all be inside here. Signal conditioning then to give you an output DC, nice DC output voltage is all embedded in this device. And that's what type of LVDT we have here. So this shows this LVDT being used in the lab as we might use it. We have a cantilevered beam with some strain gauges that we'll talk about shortly, and we put tip loads, and to measure the deflection, this core sits on the beam, and as it moves we can then measure the deflection of that beam. So again, LVDT is very common. You see them used quite a bit in a lot of different types of experiments and apparatus, sensors, and so on. We've recently started using another kind of displacement sensor in the lab to measure, in this case, beam deflection, and this is a non-contact type sensor. The LVDT core sits on the beam. The nice thing about some of these laser-based sensors is that they're non-contact, and they use position-sensitive detectors. These PSDs use a photo effect, and in a sense, what these devices do is detect the position of an incident beam, and from that they can infer by measuring the ratio of the currents out of this device, what this distance is, and then how this. Then I'll show you shortly how the device is designed that can be used to infer position. So let me show that to you. So a typical device might use some kind of infrared LED. Say you're measuring a distance, you want to measure this distance L0. So by using basic geometry, where that incident beam falls on this PSD, this X value can be inferred by measuring these currents, and at the end of the day, this distance L0 can be extracted from those basic measurements, and that's described here. You see there's lots of devices out there that you can buy in terms of the basic PSD sensors. They're also ready-made sensors. So actually the one that we use in the lab is one made by Keyence, and you can see the sensor head for this device uses this triangulation method, and the actual PSD is mounted inside this head, so you don't see any of that. And this is actually the extracted from their specification page. You can see that it's this device that we have. You have to have a standoff distance of about 20 to 45 millimeters, but the range of measurement, in other words, as a surface moves, it can detect motion over about 25 millimeters, and it has a resolution of about one micrometer. So you can detect very, very small changes in position. And so we'll be using this device in the lab. Now moving on to force sensing. These are very common force sensing methods. You've seen spring type gauges, and the interesting thing about all of these is as you can see, they all infer force measurement from a displacement, right? Even the scale here, you use calibration weights, and when you're balancing, so it's basically like a null measurement. This is a one that I found online. The rubber band here is acting just like a spring in any of these force gauges. So the displacement here is inferring force, right? So this is the same way most force sensors work. So we're going to be looking at electromechanical force sensors, and in those cases, you put a force in, and we want a measurable voltage, and that's why we're going to be using strain gauges for this. There's a lot of different types of strain gauge force sensors that you can find out there. This just shows one example. Also, the same kind of principles can be used for torque sensors. Actually, this is an optical inline torque sensor that uses optical methods to detect how much displacement, how much twist there is in the shaft. And you can find force sensors used in a lot of different products. This is a postal scale that I opened up, and you can see there's a little beam in here. And these beams in these postal scales, and a lot of scales, bathroom scales and so on, most of them are strain gauge based. And they actually look a lot like this little beam. This is interesting. You can buy this postal scale that has a beam scale, a sensor in here for about $30, and this again, the quality might be higher, but you can also buy them from this one's actually from Omega for $165, so it's quite a big difference in here. And you can also buy torque wrenches that use strain gauges as well. So you see force and torque sensing devices, sensors embedded into consumer products this way. So again, the point I'm making, force is typically inferred from displacement sensing, and you could use springs, you can use strain gauges. The need though is to extract some signal that you can then use to infer force or torque. And also you have to have an understanding both of the electrical, electromechanical conversion as well as the structural design. So we'll talk a little bit about that. As I mentioned, strain gauges use a piezo-resistive effect. You can also use, there's a lot of force sensors out there that use piezoelectric elements. These are crystals or ceramics. There's a big difference between these two. And there's also some sensors that can use contact or not. There's actually force sensors that are based on, have LVDTs embedded in them. So they use an LVDT to measure the displacement, and with a spring can infer force. But these two I want to talk about, the piezoelectric force sensors that you'll find, not as good for measuring, say, DC type forces, which when I say that, I'm talking about like a constant force. So like you wouldn't see a crystal or ceramic piezoelectric type sensor in a bathroom scale where you wanted to measure weight. Or if you want to measure anything like a constant force, you want to rely on those cases on strain gauges. So here's an example of a device for measuring, say, a keyboard force, and I just wanted to show you, you can make this very elementary. You want to apply a force, say, on a keyboard. I built this a few years ago, and use a known spring value. If you can measure the motion of these two pieces, this shaft can move with the key, and then you can push down on this part here, and by measuring that deflection, that distance, you can then infer force. A real simple type of force measurement device, and the idea is you can make these if you can understand, again, the relationship between force and displacement and the structural design, in this case a real simple spring. The most common type that you might see out there are beam type configurations, and again, the reason is because you can make things very stiff, which is nice, but the beam structure and geometry is easy to understand. The geometry is easy, the analysis is well known and understood, and you can mount strain gauges on these easily, and you can configure them in a lot of different ways to measure a lot of different kinds of quantities, either force or torque or shear. So to give you an example, like if you have a tip-loaded cantilever, we have a good understanding of the deflection of the tip of that cantilever, and we can relate the stiffness, which tells us something about the relationship between the force and displacement. We can relate the stiffness to very simple and well-known relationships. The Young's modulus, say, the area moment of inertia and the length of that beam. So beam configurations then become very common in designing force sensors. And this just summarizes some of these. You can have bending configurations, axial, beams and shear. And so the strain gauges here are mounted in a different way. And then you can also have a shaft and torsion. You can mount strain gauges and also measure then for measuring torque, say. Come back to some of these shortly. This table is very cluttered. There's a lot of information here. When you download the slides, if you ever need to look at this, but the basic idea is you have axially loaded beams here, you have cantilevered beams here. The bottom line is sometimes you mount strain gauges. For example, this one here, this very top one, you should see one strain gauge mounted. This is a beam in bending. The problem with this configuration is, and there might be cases where you might have to use this, this strain gauge would be sensitive both to axial load. So if you had any kind of load on here that was in the axial direction, or if you were torquing this and twisting this beam, that strain gauge would be sensitive to those loads. And let's say you only wanted to measure this tip load, you only wanted to measure the bending strain, then that would not work very well. Also, it could only be compensated for temperature, which is an issue. As these temperature changes, we know resistance changes, so you need additional strain gauges in the bridge to compensate for that change in strain. Okay, very subtle. So what this table does is show you different ways that strain gauges can be mounted. I really want you to mostly focus on this what we'll call the full bridge configuration, which is this bottom one here. And what it has is this has 2 strain gauges on top and 2 on the bottom, and they're wired as a Wheatstone bridge. And the nice thing about this, if you look at these 2 columns, is it's compensated both for axial and torsion load. So if you have this configuration, you put an axial load, this beam will not respond to that. You won't see any change in the output. Similarly, if you twist the beam, it's insensitive to torsion, so it's compensated for this. It's also compensated if it starts getting hot and the strain is induced due to temperature. You won't see any output due to temperature effects. So full bridge configurations tend to be really nice for this reason. Okay, so we're going to focus on that. And so here, this slide summarizes really common way to configure the 4 strain gauges as a full bridge. The output voltage, you put in an input voltage of ES, you measure the output. If you recall, if you have this null condition, then this output is 0, right? We're not interested in that. We're interested in what happens when we load this and the resistance values start changing. It's that change that we're concerned about when we have some strain. So we have a null condition and we apply the load. These resistances change. It can be shown that that change in voltage per unit input voltage V, this is a constant, but this delta depends on the changes of each of those resistors, and that falls out into, for this full bridge configuration, it falls out into this really nice relationship where you have the gauge factor, remember that, and each of the strains of the 4 strain gauges in this bridge. So if you mount these carefully, you can get some really nice relationships. So for example, if you have E1 and E4 on top as shown here, right, they're both going to be in tension. E2 and E3 are going to be in compression, so they're going to have a negative sign. So the strains also will be about the same as 1 and 4, right? And so what you have, and think about this, these E2 and E3 add up and they're the opposite sign, so you have a 4 times factor here. In other words, this equation will give you dV over V will be equal to G, right? G times epsilon, where epsilon will be the strain at this point. Okay, so that's the nice thing about this full bridge, as shown here, is it gives you a 4 times multiplier here. And this is the configuration we use in the lab. So I like to summarize it with this little picture. You know, the basic strain gauge measurement system in a block form. You have some structure and some load, but it gives you strain. You put that through a real simple relationship, right? The gauge factor, the resistance of the strain gauges, and you get a delta R. That delta R is put into a bridge, and the output, you get an output voltage, right? You need a bridge. You need signal conditioning on the strain gauges to give you this voltage, right? You're converting, instead of measuring changes in resistance, you want to measure changes in voltage, right? Then you need an amplifier. These voltage changes, not only the resistance changes small, voltage changes typically are, tend to be in the millivolt range. So you need a nice clean amplifier here. And so this amplified voltage is typically what then you end up sending to your measurement system. Here's a laboratory setup that we're going to use. We have an aluminum cantilevered beam. I call this a beam sensor, force sensor. It does deflect quite a bit, more than a good force sensor would. Typically you want force sensors to be a little stiff, and that's the challenge in the design of a good force sensor is you want it to be soft enough so that there's strain that can be detected, but you want it to be sufficiently stiff so that it doesn't deflect too much under load, right? So it's that balance that the design requires you to be careful with. This is a setup that's designed to give you an opportunity to use and learn about strain gauges, as well as some kind of displacement measurement. Again, we in the lab may only have time to use the laser sensor. In the past, we've used the LVDT, but the configuration is fairly easy. You run calibrations. Again, the exposure to the setup is what we're after. Just to show you what the typical amplifier might look like, this sensor here represents that full bridge, like you might have on that cantilever beam, and the particular amplifier that we are using has connectors for outputs that go to power the bridge. So it's kind of hard to see, but power sent to the bridge from this device here, and then the output across the bridge is sent back to the device and goes to an instrumentation amplifier and a filter, so you get a nice clean output. So the output from this amplifier is what we'll then send to our DAC system, right? So the nice thing about a device like this is it provides the power for the bridge as well as the amplification. You do require AC power here. So again, what you're going to do in the lab is you're going to learn how to set up and use the strain gauge beam, run some calibrations, and test for force measurement. We're going to learn about using this laser displacement sensor. It's proper and safe usage, and then if time permitting, you might the TA may give you a quick demo with the LVDT, but given the time constraints that we have, we may not use the LVDT. We also, again, want to continue having you experiment with LabVIEW, and we may introduce you to using a calibration VI that will automate the collection of some of the data. This will give you an opportunity to see the design of a different LabVIEW VI for that purpose, rather than just a sort of rudimentary collection of calibration data. At least, how would you design a nice virtual instrument that automates the collection of data and then also generates the calibration curves for you? So we are going to experiment with showing you how to program a VI of that sort. We'll probably give you the VI and have you make some small changes to it. Okay, and then also I'm going to ask you in the pre-lab to think a little bit about some of this design, the mechanical design, because some of the data that you'll extract, we're going to ask you. We discussed very briefly how the stiffness of the beam is related to Young's modulus and to the geometric properties of the beam. So you should be able to measure information from this setup so that you can actually estimate the Young's modulus for this beam, and it kind of gives you a sanity check. Does that number make sense based on the data that you took? Okay. All right, so in summary, I really want you to walk away with a sense of how force measurement really, there's an intimate relationship between, force, displacement, and stiffness, and all of these sensors. Um, Strain gauges are, very very common for many of the sensors that are used for force and torque measurement. Think about also how all of these sensors require signal conditioning. The particular type of signal conditioning here we're talking about that you're not going to spend a whole lot of time doing analysis on circuits, but at least be familiar with the fact that you require the use of a Wheatstone bridge, and also um, be cognizant of what that's doing. That's converting a resistance change into a voltage change, and then that voltage change has to be amplified. So there's amplifications required to get a measurable signal. So I want you to be aware of the kind of instrumentation that's required to make strain gauges work, in case you have to ever go out there and spec out a system, and you need to know what to buy and why. Again, strain gauges are core knowledge for mechanical engineers. I always like to say, you're sitting around in a group of engineers, and anything has to, anytime some strain measurement has to be made, strain gauges have to be understood. They're going to turn to the mechanical engineer in the group, so it'll be good for you to have at least some of the basic working knowledge. Okay, so in a follow-up video, I'll talk a little bit about the pre-lab, show you some of the working VIs maybe that we're going to try to experiment with in this coming lab. All right, thanks.